Okay, this will be the part two of the video regarding the derivative of functions using chain rule. And again, the first video was already uploaded, but it seems that half of the second half of the video doesn't have an audio. That's why I'm recording the last part of the first video that I recorded, which doesn't have um, an audio. Okay, so that's example number three. That's method two. So I will be doing it again to make sure that you would understand the way I solve problem number three using another methods. All right, two more methods. So let's start again. So again, we solve this example number three using method one, all right, the direct method to solving the derivative of the function y. And again, if you're going to look at the given function, now you can simplify, or we can easily simplify the given expression by distributing the exponent to the numerator and denominator, right? So that's what I did in the first part of the video, and that's what I call method two. And again, our answer is this. So we should be getting the same answer once we deal with methods two and three. So let's start with method two. So in method two, let me just, yeah, or here we go. So method two, we have a y is equal to, again, we're using x cubed over x plus one cube, okay? I changed the given because we use x cubed in method one. So let's use the same given. So in method two, I will be distributing the exponent first before I differentiate, all right? So as we could have another way to differentiate this function. So this becomes x raised to 9, okay, and x plus 1 raised to 3. So this one is quite simpler compared with the original given because we have only a quotient of two polynomials, x raised to 9 and x plus 1 cubed, right? So let's now do the derivative, and let's differentiate this using the quotient rule. That's law de high minus high de low over law or the law square. So we have the denominator, capital denominator, cube, and let's differentiate the numerator. That's 9x raised to 8. I'm not going to explain the basics, and I hope everyone already know how to do the derivatives of these functions or expressions, okay? So next, low de high minus high de low. That's x raised to 9, high de low. So that's the derivative of x plus 1 cubed. There we go. So we need to differentiate this. Okay, again, we are still differentiating the second factor of the second term. This one, I haven't differentiated yet since I want to make it more organized. Okay, and this is all over by x plus 1. Let's go back to y. Okay, here we go. By x plus 1 cube, and it should be squared based on the formula for quotient rule, correct? So we can simplify this one. This is 9x raised to 8 times x plus 1 raised to 3 minus x raised to 9. And let's differentiate this x plus 1 cube using chain rule. So we have 3 times x plus 1 square. As we said, put the exponent as a base or coefficient and copy the base, then subtract the power or the exponent by 1. So that 3 minus 1 becomes 2. And differentiate the base, x plus 1. So the derivative of x plus 1 is 1 plus 0. All right, and let's copy the denominator. That's x plus 1 cube raised to 2. That's x plus 1 raised to 6. Okay, so we can simplify the numerator now. Let's move on to the next slide. That's y prime is equal to, let's copy, 9x raised to 8 times x plus 1. Oh, here we go, cube, minus let's simplify this. This becomes 3x9, 3x raised to 9 times x plus 1 square times 1, that's, oh, I locked parentheses here. So x plus 1 square times 1 is x plus 1 square. So x plus 1 square. Here we go. So again, the denominator is x plus 1 raised to 6. Oh, sorry. Oh, 6. Okay, this is 6, all right? 6. Okay, here we go. So let's simplify the numerator. The numerator can be simplified, or let's identify the common factors of the numerator. We have 3x raised to 9, okay, or x raised to 8, and x plus 1 cubed, x plus 1 square. So therefore, our common factors here are 3x raised to 8 and x plus 1 square, right? So let's do that. Let's factor out these factors, okay, to simplify the given expression. And we have, so we have 3x raised to 8 and x plus 1 square times, so let's divide. So 3x raised to 8, this becomes 3, and x plus 1 square, so this becomes x plus 1 minus 3x raised to 8 was already factored out, so we have x here, and x plus 1 square was factored out, so this becomes 1 all over x plus 1 raised to 6. So let's simplify again this expression, this one. All right, so I'll copy 3x raised to 8, x plus 1 square, and this is equal to what? 3x plus 3 minus x, that's 2x plus 3, all over x plus 1 raised to 6. Here we go. Now, if we're going to look at, check the expression, guys, we can still factor this out. We can cancel out x plus 1 square by x plus 1 here. So this becomes 4, correct? 4, 6 minus 2 is 4. So here we go. So we got final answers. We have now 3x8 times 2x plus 3 over, or a lower, or over, sorry, x plus 1 raised to 4. So this is our final answer. And let's check if it's equal to the answer or final answer in our method 1. Let me check my audio. Okay, here we go. All right, so we have 3x8. Let's check. 3x8, 2x plus 3, correct? 2x plus 3, and x plus 1 raised to 4. Let's check if we have the same answer. X plus 1 raised to 4. Here we go. So which means, guys, that we have already found the same answer with the use of second method. So which means it implies that whatever we do, as long as we're not violating any rule, mathematical rules specifically, then we can do it that way. Okay, we're allowed to do that. Okay, so in method 3, here we go. So let me just, method 3, in method 3, we'll be using Leibniz's way of solving the problem, all right? Let's see if it's shorter than method 1 and method 2. So our function is y is equal to x cubed over x plus 1 cubed. Okay, so it's very obvious that it is composed of two functions, the inner and the outer, or it is a, y is a composite function. So let's identify those functions. We have, let u of x is equal to x cubed, which is the inner function, x plus 1, and our f of x is equal to u cube, right? This is our u and this is our cube. So here we go. And Leibniz said that to get the derivative of a composite function, we have, or this can be, before we do this, let's rewrite this in terms of the function that we assigned. So f of u of x, here we go. So with the use of the chain rule for the composite function, we have y prime is equal to f prime of u of x times the derivative of the inner function, which is u of x, or u prime of x. Here we go. So which means this is equal to, oh, this one is in our method 1, right? So by limits, this is equal to df of u with respect to u times, all right, du of x with respect to x. So this is what we're trying to use, correct? So we need to identify the derivative of f in terms of u and the derivative of u in terms of x. So we have, we need to differentiate first the f, all right, the function f. So in this case, let me just, there we go. Let me just assign a space. So let's identify the derivative of, let's write our solution here. The derivative of u of, f of u with respect to u. And again, our u here, or f here, is this. All right, so we need to differentiate this. So this becomes 3u squared, correct? So we need to bring down the exponent as a coefficient of the function and subtract the exponent by by 1. Sorry. So this becomes 3u squared. Or with the use of chain rule, we can still differentiate u by signing it as u prime, but still, it will still result to 3u squared. All right. So it doesn't really matter if we're going to do this because it's just equal to 1. And we already found the first factor here. Now let's find the u here. Okay, so let's make use of the second slide or the next slide. So u of x is equal to x cubed over x plus 1. So we have du of x over dx is equal to, since this is a quotient of two polynomials, then we can use the quotient rule in finding the derivatives of u, right? So we're going to use the modify x plus 1 minus the derivative of the numerator, that's 3x squared, minus high the low, that's x cubed, times the derivative of the denominator, that's 1 plus 0, all over the square of the denominator, that's x plus 1 square. And this is equal to, let's simplify, this becomes 3x cubed plus 3x squared minus x cubed. This is 0, all over x plus 1 square. All right, so we have, we need to simplify this. This becomes 3x cubed minus x cubed, that's 2x cubed plus 3x squared all over x plus 1 again. Sorry for that, for this. 3x plus 1 square. Okay, here we go. And let's write it that here. So I can factor out the numerator by x squared. So x squared times 2x plus 3 all over x plus 1 square. All right, so this is our u prime of x, or this is equal to du u of x over dx, or with respect to x. So we're now going to combine these two with the use of Leibniz way of solving the derivative, okay, of using chain rule. So df of u over du times du of x, sorry, extra parenthesis, dx. And let's make use of the values that we got from the derivative of u. The derivative of u is 3u squared. 3u squared times. And the derivative of u of x is what? Let's du squared. There we go. X squared, sorry, du squared du of x with respect to x, that's x squared plus 2x plus 3, x squared times 2x plus 3 over x plus 1 squared. So this is what we got, right? Okay, oh, sorry. I think I forgot something. Uh-huh. Okay, here we go. Yeah, correct. X squared. Okay. Now, again, we have a u variable here, and we knew that u is not part of the given problem. So we need to express u in terms of the original variable. So we use u, this one, the x cubed over x plus 1. Okay, so 3 x squared, is it x squared? Sorry, x cubed. X cubed over x plus 1 raised to 2 times x squared to x plus 3 over x plus 1 square, something like that. Okay, so let's simplify here. Okay, so this becomes 3x raised to 6. We're dealing with the first factor here, and x plus 1 square, right? And let's simplify this. This is x squared to x plus 3, or we're just copying to simplify, x plus 1 square. Here we go. So let's multiply, okay? Combine like terms if we can. So we have 3x raised to 8 times 2x plus 3 over x plus 1 raised to this one, x plus 1 square, x plus 1 square, that's x raised to 4. Okay, so we got the final answer. And let's check if we got the same final answer with the use of methods 1 and 2. 3x raised to 8 to x plus 3, 3x raised to 8 to x plus 3, x plus 1 raised to 4. Here we go. So we get the same answer in method, or with the use of method 3, all right, with other methods 1 and 2. So which means whichever method we use, guys, we will get the same answer. Okay, as long as you're not violating any mathematical rules or properties here. Okay, so you may decide which type of method you're going to use. And I prefer and I advise everyone to use the shorter or the shortest method. And at the same time, the method that you are used to using, because you might be using the shortest and the fastest, but it will give you a lot of errors once applying or employing this method, okay? All right, I hope everything is clear. And let's proceed to the next example. Before that, let's first discuss the power rule combined with the chain rule. So it is a combination of power and chain. So it's a combo, right? So power rule combined with chain rule. So that's power, chain, rule combo. Okay, power chain combo. And how do we use this rule? Right, if n is any real number, take note of that, real number, u is equal to f of x is differentiable. Of course, it should be, or else we don't need to differentiate or to find the derivatives of the given function. Then the derivative of u raised to n, this one, with respect to x, u is expressed in terms of x, is equal to, put the exponent to the coefficient, copy the base, and subtract the exponent by 1. And again, as we always do in our previous example, differentiate the base, the u, whatever it is. It could be the simplest function x or whatever. Still, you need to do that, all right? For you to make sure that you're doing it properly and correctly, and u over x. Or the other way around, this is what I like. This is more direct. Okay, the derivative of f of x raised to n with respect to x is equal to n times the base, exponent, and minus 1, and the derivative of f of x. Okay, here we go. So let's use this rule in solving example number 3. Not just these rules, but all the rules for the properties or theorems in finding the derivative of the given function. So number 3, let me read. find the equation of the tangent line in slope-intercept form to the graph of f of x at x is equal to 2. Here we go. So we were given some conditions in order to solve for number 3. So we're solving for the equation of the tangent line. Tangent line. Okay, and in terms of y is equal to mx plus b, because this is our slope intercept form. All right, so let's use the other slide, or let's go to the next slide. So f of x, let me copy. I want to express this radical in terms of exponential because it's quite easier to deal with. Okay, and you can easily see the exponent. So this is 2/3. All right, x is equal to 2. Okay, so the first step to do here is step 1, solve for f prime of x. And once we solve for the derivative of the given function, we are now solving for the slope of the tangent line, correct? At the, sorry, it's not supposed to be. So this is our x. There we go. And our x here should be at 2. So let's differentiate the function f. So we have f prime of x is equal to, this is a complex exponent, exponent function, or a composition of function of x squared plus 4 and x raised to 2/3. But I will not be using Leibniz's way of solving it. Let's solve this directly, okay, or differentiate it directly. So we have 2/3, copy the base, and exponent 2/3 minus 1. And don't forget to differentiate the base, x squared plus 4. All right, I just copied the base. And of course, don't forget to put the symbol for differentiating that base. Okay, so don't forget this, guys. Sorry, excuse me. Which means that we're going to differentiate this. All right, and we haven't done that yet. Okay, so let's simplify this. So we have 2/3 x squared plus 4 raised to negative 1/3 times 2x plus 0. There we go. So let's copy, let's simplify. So we have 2 times 2x over 3. And this becomes x squared plus 4 raised to 1/3. Correct? So this is our f prime of x. Okay. Or we can rewrite this in this form. F prime of x, or the derivative of x, equal to 4x over 3, the cube root of x squared plus 4. All right. So again, we're going to solve for f prime, or the slope. So we're not yet done. So part of step 1 is we're going to solve for the slope at x is equal to 2. Or this is equal to m of the tangent line at 2, which is equal to, let's use the given. So 4 times 2 times 3, and the denominator is the cube root of x squared plus 4, the cube root of 2 cube plus 4. Sorry, this is square. All right, this is 8 over 3. And this is 4 plus 4, 8. The cube root of 8 is 2. And this is equal, this is 2. This is equal to 4/3. So the slope of the tangent line is equal to 4/3. And we know that we're looking for y is equal to mx plus b, which is equal to y is equal to 4/3 x plus b. Now at this moment, guys, we're going to solve for b. Okay, we're going to solve for b, but for us to solve for b, we need to use the value of x and the value of y. we have already a value of x as part of the given, but we don't have the value of y yet. So we need to solve for y first, all right, to solve for b. So here, to solve for y, we have x, y. Our point is at 2, and y. We don't have y yet, correct? So for us to solve for y, we need to solve for f of 2 using the given function, cube root of what's that? 2 square plus 4 raised to 2, correct? I'm just using, guys, the given function here to solve for y when x is equal to 2. So this is equal to cube root of, this is 8 square, correct? Or we can write this as, what's that? 8 raised to 2 thirds. And this is equal to 4. Am I correct? This is equal to 2 cubed times 2 raised to 3, or raised to 3 pala, sorry. Cancel, yeah, it's equal to 4. So f of 2 is equal to 4. Therefore, this is 2, 4. This is the point where the tangent line is intersecting the graph of f. All right, so let's use this equation to solve for b. So y is equal to, the slope is 2x plus b. And again, we knew that the point is 2, 4. So 4 is equal to 2 times 2. Oh, here we go. The slope is not 2, it's 4 thirds. Oh my. Okay, so this is 4 thirds. 4 over 3. Oh, I find a way. 4 thirds plus b. Yeah. All right, so this becomes what? 8 over 3. 4 minus 8 over 3 is equal to b, and b is equal to 12 minus 8, that's 4 over 3. So therefore, y is equal to 4 thirds x plus 4 thirds. So this is our equation of the tangent line to the given curve. All right, so this is our solution or final answer to the given problem. Okay. And I hope you got the same answer. All right. Okay, here we go. Now let's discuss a problem which is an application of derivatives. All right. So here in example number 4, let me read. The total number in thousands of bacteria present in a culture after T hours of growth is given by this function. Okay, the growth was already identified in terms of a function, n of t. This is the number of bacteria at a certain given time t. And this problem was derived from here, so 1996. And again, this problem was presented in one of the modules of Math 5 under PSI. So here we need to find the derivative of n with respect to t, and at what rates the population of bacteria changing from t is equal to 8 hours, 11 hours, and so on. And here, we're going to answer letter C as well. So, but before that, let's answer letter A first, okay? So letter A, our n of t is in terms of 2t times t minus 10 square plus 50. All right, so we're going to differentiate this to solve for A. So we need to solve for the derivative of n in terms of t. So we can differentiate this. This is a product, okay? 2 factors, therefore we're going to use the product rule. Or if you want, you can expand this and then try to find the derivative term by term. But let's use the derivative of using the product rule. Okay, so we have 2t times the derivative of this, which is 2, copy the base, and 2 minus 1, of course, and differentiate the base. T minus 10, that's 1 minus 0, plus All right, copy the second factor, t minus 10 square. And what's the derivative of 2t? That's 2 plus the derivative of this, which is 0. Okay, I hope you got it right. All right. Okay, so again, just want to make sure we take the derivative of this using product rule. Okay, so let's simplify. This becomes 2t times, or this becomes 4t, 2 times 2 times t minus 10 raised to 1 times 1, that's it. And this becomes 2t minus 10 squared plus 0. All right. And I can factor out 2, this is t. T10, sorry. I can factor out what? 2t minus 10. Okay, these factors, this one and this one. So I have 2t minus 10. All right, so this becomes 2t, and this will be canceled, plus 2t 10. We have t minus 10. Correct? I hope I'm not mistaken. All right, so let's simplify this. We have 2t minus 10 times, let's simplify, 3t minus 10. Here we go. So this is our final answer. Okay, and let me recheck first. Let's see if I got or committed errors. All right, I think we got it correctly. Okay, so we have this answer. Okay, let's check that if we get the correct answer. Let's try another method. We want to make sure because we will be solving 2 more problems after this. So we have, the problem is 2t times t minus 10 square plus 50. If I'm not mistaken. Yeah, okay. The other way around is to expand, okay? Again, this is just, I just want to make sure that I got it correctly, okay? The derivative of the given function and in terms of t. So this is 20 t plus 100 plus 50. This is my n of t, the function of n. So let's no need to differentiate yet. Sorry, let me just continue. I want to distribute to t. So 2t cubed minus 4t squared plus 200t plus 50. Yeah, okay. So I think we're now ready to differentiate n. 60 square minus 80t plus 200. And this is 0, right? So we have 60 square minus 80t plus 200. Let's see if we'll have the same answer. Oh, here we go. So this becomes, let's try solving this one, guys. Let's see if we'll have the same answer. Okay, here we go. So this is 2, I'm just rechecking, okay, 3t square minus 10, 30, 40 minus 40t, 100. And if we go and simplify, 60 squared minus 80 plus 200. Oh, here we go. We got it correctly. All right. Okay, so it shows that we can solve it in different ways, all right, or in 2 methods. So we have already solved letter A, and let's move on to letter B. Letter B, the problem in letter B, or the question in letter B is, at what rate is the population of bacteria changing when t is equal to 8 and t is equal to 11 hours? So here we're solving for the value of the derivative of n at 8 hours. Okay, so we have 6 times 8 squared minus 8t times 8 plus 200, 64. Oh my, 64. It will test my computation skills. So, oh my pen is afraid of multiplying. 64 times 6, there we go. 24, oops, 24 to 6384. So 384, if I'm not mistaken, that is 638. Yeah, minus 640 plus 200. So 200 plus 384. What's that? Let me just 640, 584, right? 584. So 6, 3. This is 5. This is 5. 13. Yeah, 56. So the answer here is 56. Negative 56. So it means, guys, when after 3 hours or 8 hours, now the population, all right, of the bacteria is negative, which means the number of bacteria is decreasing by negative 56. Sorry, by 56. Okay, per, what's that? Per hour. Okay, that's per hour. Now let's move on to how about if the time is equal to 8? So n prime of 11 is equal to, let's review, 860 square. 6 times 11 square minus 8 times 11 plus 200. Let's check. 60 square minus 80. Yeah, here we go. So this is 121. 121, that's 121 to 721, correct? 721 minus 880 plus 200. Here we go. So this is 921 minus 880. 921, 881, 8. So that's what? 41, if I'm not mistaken. So the after 11 hours, guys, the rate, okay, the rate of change in the number of bacteria is 41 bacteria per hour. Okay, so that's after 11 hours, or when T is equal to 11. So it's positive. Therefore, there is an increase of bacteria at T11. However, at T8, there is, what's the value again? 56, negative 56. There is a decrease of bacteria, 56 number of bacteria per hour. Okay, so I hope we already solved letter B and you already understood what it means. And letter C, one of the answers in part B is positive while the other is negative. What does this mean in terms of population of bacteria? Oh, we already explained that, right? So again, let's answer letter C. When P is equal to 11, the number of bacteria is increasing by 41 bacteria per hour. And at T is equal to 8, or at 8 hours, or after 8 hours, the number of bacteria is decreasing by 56, okay? Number of bacteria per hour, okay? That's what it means, all right? That's how we use the derivative. It's very good, right? Okay, we can easily identify the rate of change of a given function or given situation at specific value of time or specific time. Okay, so we're done with example number 3. Let's move on to example number 4. Here, suppose f and g are differentiable functions with g of 0 is equal to negative 2 and g prime of 0 is equal to 2 and f prime of negative 2 is 1/2. And we are going to find h prime of 0 if h is equal to f circle g. So let's write the given f circle g. And this is just equal to f of g of x, correct? Okay, so since we're looking for the value of h prime of 0, so we need to solve for h prime of x first. And this is equal to, based on the definition of the derivative of a composite function, is equal to f of prime of g of x times the derivative of the inner function, which is g prime of x. Okay, and we knew that we're solving for h prime of 0. So therefore, f prime of g of 0 times g prime of 0. Now, what is the value of g of 0? G of 0 is negative 2 times g prime of 0 is 2. And what's the value of f prime of negative 2? That's 1/2 times 2 is equal to 1. So therefore, the answer is 1. All right, so we got it, okay? So make sure that you knew what the definition or the rule for the derivative of a composite function, okay? So next, oh, we have a next topic which is called chain rule involving exponential and logarithmic function. And this will be discussed on our next video, part 3. So please watch the next video for you to learn about these topics. All right, exponential logarithmic functions. Okay, bye.